initially, and then a little bit later on, how we're going to try and apply that to VLEO systems and integrate that a little bit with the business modelling approach that Daniel will give you an introduction to later. So I'm going to start off with a little bit of a description about systems, then a description of models very briefly, an example of a simple systems modelling kind of tool, something that I did in my thesis, and then the actual implementation for VLEO systems. So what I have on the screen now is a simple hierarchical example of a space system. So you might recognise many of the different components in this diagram. So maybe the orbit and configuration, maybe the ground segment and some parts to do with that. The launch, obviously, to get it up into orbit. The space segment, so we can separate that out into the payload, and then the bus, the platform that serves the payload, and then these operations that we have to do to perform the mission to launch it, and end of life, of course, which we need to consider. And we might consider this to be a simple system. More complex systems might have many more boxes in the hierarchy. But it's not just as simple as this. We have many things that we have to consider alongside this. So we have the requirements or objectives, or we might consider to look at value in this case. We have many different stakeholders that are interested in how this will perform and the kind of requirements that are fed into this. We have the complete life cycle to consider. So this doesn't just mean the operations, but we might look at the manufacturing or even down to the component suppliers. We have interactions or dependencies between different subsystems, between the payload. So there's lots of cross-links all across this hierarchy. And of course, it's very multidisciplinary, if we can tell by everyone who's interested in the room here. We all come from very different backgrounds. So, how can we define our system? Well, we can take a traditional description of it from the NASA Systems Engineering Handbook. So, a construct or collection of different elements that together produce results not obtainable by the elements alone. A very traditional description. We can consider it as almost anything. So a little bit of a flippant description from Elon Musk, but he doesn't like calling things systems because everything is a system, including your dog. And he's got a very good point. Pretty much everything is a system when you try and decompose it. But fundamentally, for what I'm trying to convey, is that we can represent systems as either a network of interconnected subsystems, or systems, or as components or models. And that's where modelling comes into this. So a representation of a system might come in a form like this. So we have various things across the diagonal, which may be subsystems, they may be models themselves, and we can indicate connections or interconnectedness between them with the nodes on the diagrams. And in this case, at the moment, I have everything connected up to everything. And it's our challenge to figure out where these things are connected, how they're connected, and then also to perform the links of information across these connections. So in this case, in this diagram, we can feed forward information between the different blocks over the top. But then importantly, we also need to know whether we need to feed back information back up the chain. And depending on how we want to do this, we can reorder blocks to make this more or less efficient. And if we still have these feedforward and feedback connections, then we actually enter some iterative loop. And that becomes important later when we actually try and do full system design and when we want to try and consider optimization as well. Within each of these blocks, we might also then have lots of subsystems. So for the example given here, for a space system, we have the payload, we have telemetry, tracking, control, power, communication, structure, attitude determination, so on. And we have dependencies and interactions between each of these systems. So in this case, we might have dependencies going across the top. So for example, our payload might be dependent on the power that we have available on the platform, on the attitude determination and control system, and on the onboard data handling system. But then we also know that our payload will interact with all of our other subsystems as it will drive the design of the spacecraft. Okay, and then we have all of these different interactions between all of these subsystems, which we have to consider going through our design. So as we move on later to the VLEO, a lot of our work is about identifying what all of these interactions and dependencies between the different subsystems are and between the different design elements, so that we don't lose certain aspects of our design. And by characterizing as many of these as possible, we can actually drive towards a much more optimized system. So, moving on to the next level down, what is a model? So, in our modeling, we want to basically simplify or abstract our system or an object to a fundamental level. And we can do that possibly graphically, we could do it mathematically with equations, we could do it heuristically using data or information from, for example, past missions or drawing relationships between certain variables. We can do it with spreadsheets, or we can do it with more complicated programming, MATLAB, Python, C, or we can do simulations now. So modelling now is moving into potentially FEA, FEM, CAD design, and computational fluids, DSMC tools as well. In the early design stages, we try and keep it as simple as possible, so it tends to be equations or relationships, but as you move further into the detailed design, you might use much more complicated tools. But essentially, we want to build them from the fundamental elements or relationships, so that we're building everything from the ground up. And just wanted to make a small point on the way in which we see the kind of systems modeling discipline moving. So in the past, it used to be very document-centric. So it could be blocks of text describing how something would work, or a diagram. It could have been a very simple spreadsheet, which in itself is a model, but maybe held by one person and some information communicated to someone else. These documents might have been discrete, disjointed, owned by one person, communicated by telephone or email, potentially. And we'll give you a snapshot of a single component or a design at any given time. And you'd have to work around all of the people in your disciplinary team to build up a single point design. You could then look at how well that performed, and maybe do the loop again, and you might be talking about a week, a month, several months before you'd be able to reiterate your whole design on your space system. Nowadays, it's moving much more to an integrated model, so you have a single, possibly called system designer, who would collate all of the information, all of the models together. Each of these models might be owned by a certain subsystem modeler, maybe within a single company, maybe operating somewhere else. But you get a single point of truth when you integrate all of your models together. And you can work through this much more quickly. You can change the model and bring a new one in, update everything as quickly as possible, depending on how long you have. If you're doing simulations, for example, they might take a little while to propagate through. And you can actually work through these design loops much more quickly. And if you can vary your inputs to your design loops and look at, hopefully, a useful metric in the output, then you can actually look at optimizing these systems much more quickly and exploring a lot more of the design space that we have available. So this is very much the kind of system that we see everything moving towards. So now I'm going to present a quick example of a system modeling process for a propulsion subsystem, particularly for mass of the system. So we could look at power, we could look at the thermal effects, we could look at the structural, and across all of our different subsystems, we would work to put these together to look at the overall view of a spacecraft or system. But in this case, I'm just going to look at propulsion and the mass of that system. So this is a representative diagram of that system. So we have on the left-hand side some external inputs. So we have the mission analysis, we have a delta V budget coming from that, so this is the amount of energy we need to put in to perform maybe station keeping maneuvers, any necessary other mission maneuvers that we might want to do. We might need to have a level of thrust that we put into the system to actually affect that. And then we have an overall mass budget for the system and the dry mass of the spacecraft feeding in as well. Internal to our propulsion subsystem, we will have a database or in this case we have a database, we might actually have a design for a thruster. Otherwise, if we knew exactly what we wanted to design. We have some performance related to that. Then we'll want to calculate some parameters related to the thruster, the design of the tanks that are going to store our propellant, how much propellant we're going to need, and then we can sum all of these together to give ourselves the propulsion system mass, which we can then feed back into the overall spacecraft design. So I'm going to go through this in stages, add everything up, show you a couple of different examples of the individual models that feed into this and how we use them. So I'm going to start off with the propellant mass. And I've given some variables for our mission. So we've got a spacecraft with a dry mass of 500 kilograms. We can find this out from the basic mass budget. If we have a payload, then we can figure out maybe about how much our bus needs to weigh in the first instance, and then we can iterate through afterwards to figure out what the exact mass will be as we get into a more detailed design. I've given a representative 500 kilometre sun-synchronous orbit, and we want a 5-year lifetime in that orbit, so we can determine the station-keeping manoeuvres required to keep us in that orbit, giving us a delta V of approximately 125 meters per second over the 5 years. And maybe we want a thrust of 7,500 newtons. That'll help us characterize our thruster in the first case before we go on to more detailed design. If a priori we decide to choose a xenon Hall effect thruster, we can get an approximate ISP without knowing exactly, just taking an average of the known Hall effect thrusters available of 1,490 seconds. As we move on, we might decide to change the thruster type. That would affect our ISP, and that would propagate through this space. So this would be a case of maybe looking to optimize for different propulsion system types. So we could look at ion thrusters, or even if we wanted to look at chemical propulsion systems, coal gas thrusters, monopropellants, etc. So, to work out our propellant mass, we can go to the simple rocket equation. Some of you might be familiar with this. If not, we can take our delta V, and if we know the ISP of our system, we have gravity, and we have the log of the initial mass of the system and the final mass of the system. We can work out how much fuel we need to provide that delta V. Okay, so I've just rearranged the equation at the top to the bottom here, and if we feed in our numbers, then we can work out we need 4.3 kilograms of xenon fuel. So we can feed that into the first part of our model. Okay. Our tank design is now going to be both dependent on the mass of propellant that we want to store and the pressure at which we want to store that propellant. So I've added another parameter at the top. So a typical storage pressure for xenon would be 7 megapascals. So 70 bar, relatively high pressure, maybe storable for larger satellites generally. For smaller satellites which are deployed as secondary payloads, you wouldn't be allowed a pressure that large. So our tank design, again, is informed by relatively simple equations in the first instance. So using the gas relationships, we can work out a volume required in the tank to store our mass of propellant. So we have the volume of the tank, we have the mass of propellant, we have the specific gas constant, we have the temperature at which that's stored, we have the maximum pressure, and we have the molar mass of the propellant. And again, if we plug the numbers into this, we can work out a volume for our tank. This is a relatively small volume due to the relatively small amount of volume. Now, if we want to consider the design of the tanks, and in this case, we're going to take a very simple example of a spherical tank, very easy geometry to work with. However, we could extend this to cylindrical tanks or toroidal tanks quite easily. Then we just need to find out the thickness of the wall of the tank to store the propellant at the maximum pressure we want to consider to find out how much that tank is going to weigh. Okay? So we have a relationship for the radius of the tank with the volume. We have a relationship for the thickness of the wall of the tank with the pressure and the yield strength of the material that we've chosen. And we can vary that material and see how that changes the strength or the mass of the tank in the end. We have a factor of safety. that we need to include, otherwise we'll come out with a very, very small mass, which potentially wouldn't be able to store the propellant safely. And then we can put these down into a final relationship which gives us the mass of the tank, which uses also the density of the material that we require. And again, if we plug in the numbers for this, we can see that our tank is going to weigh approximately 1.32 kilograms. So we can add that into our model, and you can see we're building this diagram up, and we'll finally get out at the bottom the total mass. So now we can consider the design of our thruster. And in this case, we chose a xenon Hall effect thruster in the beginning, and we know the LSP, we know the storage pressure which we want to have the propellant at, and we know the thrust that we want this thruster to be able to produce. However, we might not have designed this thruster itself yet. So in the early design stages, we might use relationships of systems that have already been produced to estimate the performance of a new system or something that we could imagine could be produced. So here I have two graphs, one relating the power of the power required by the Hall effect thruster to the thrust it produces, and another which relates the mass of the thruster to the thrust it produces. And these are just very simply fitted relationships to historical or available data for low power systems. And in this case, if we know our thrust is going to be 75 millinewtons, then we can draw basically up to the curve or solve the equation to get the mass of the thruster assembly. And then of course we can add on some additional mass for harnessing and pipe work, etc. And in this case, 4.36 kilograms. So very, very simple method for estimating performance where we have kind of sparse data or we don't have design yet. So finally, we can sum our different masses together and we can get a first pass at the mass of our propulsion subsystem. Okay? And we can feed this back through into our spacecraft mass budget. So we may have already budgeted for 15 kilograms of propulsion system already, and now it looks like we're possibly coming in under budget somewhere. So we can iterate through, and we can actually see that a natural loop is created here in our system. Okay? But we might also want to vary many other parameters in the spacecraft design first. So looking back at all of the other subsystems, so power, for example, we know that the propulsion system has a very demanding power requirement if it's a Hall effect thruster, so we might look at the power requirements as well in that loop. But very simply here you can see that the loop is formed. And let's not forget about margins. Okay, so there's various guidance on how we should perform this, and this basically accounts for a lot of the uncertainty in the design and in the modelling process. So I've taken guidelines from the ECSS here. So as you can see, 20% on your system mass. So once you've basically generated everything, you put all your models together, and you maybe found a mass for your spacecraft, add 20%. If you're using at the subsystem level or at the component level off-the-shelf items, so you might hear them as COTS, then add 5% for that of the mass. If you require modifications, 10%, and if you're redesigning something completely new, 20%. When you're making calculations on propellant, we need to assume that some propellant is left in the tanks or made residual, so add 2% on the mass of any propellant. And on delta V, so where I made the calculation that for a 5-year lifetime at 500 kilometers, we needed 125 meters per second, we need to add 5% if we did that calculation in a detailed manner, so potentially using some complicated commercial software like STK, or if we're doing it just using simple relationships or simple guidance, then double the value that you've already calculated. And again, for any attitude control, double the requirement as well. Okay, so you can easily see how if we have our systems model, that we can add up the mass very quickly and it will scale very quickly as well. So the more detailed we can be later on, the better. So how can we apply these systems modeling principles to our very low Earth orbit system design in the first case? So before I presented a very simple model for a space system. Now we can move that on to specifically our VDO systems. And I guess this is where, in the discussion sessions, we might have a lot of feedback from you guys, hopefully, is how we can connect these different blocks together, making sure that we don't miss any of the interactions or dependencies between the blocks. So I've got a kind of first pass here. So you'll notice that I've eliminated some of the connections where I'm not necessarily sure that there are very strong links, but then also started to enumerate some of the other ones, so where I think there definitely are very strong interactions and requirements. But this is by no means the kind of finished article in terms of the system design. Okay? But this is before we move on to looking at actually full concepts and integrating this with business models, etc. This is all very much in the space system segment. And within the VDO spacecraft design, we incorporate a lot of the very technical aspects of DISCOVERER. So we're talking about the reduction in drag, we're talking about compensation of drag, materials, and the aerodynamic control aspects as well. So the VDO spacecraft design section is obviously very rich from the DISCOVERER point of view. Now, if we leave that for a second and think about how we actually drive towards a final design, or how we would describe the metrics of a design, we can simplify this and look at it in two dimensions. So I presented about, in the example, about mass, and we might have a mass requirement for our total spacecraft system, maybe if we need to fit on a specific launch vehicle. Okay, so if we've chosen our launch vehicle, we'll have a mass requirement. And we might also have a cost requirement from our customer or other stakeholders somewhere. And generally our objective would be to reduce both of these requirements. Okay, so to drive towards a minimum. And naturally, in the case of this diagram, we would drive towards the zero axis, or the 0 point. And we also have a point where we satisfy both of the requirements. And this would be the point at which we've achieved both the requirements, we put the minimum effort in, and this is where we stop. However, we could improve our designs by either lowering cost, or lowering mass, or lowering both. So if we can do our systems modelling, and we can enumerate lots of different designs with various different input parameters, we could change the propulsion system maybe, so instead of a Hall effect thruster, we could look at cold gas thrusters, look at monopropellants. Then we might generate a set of designs, the best of which might fall on a curve like this. And we call this a Pareto front, where we can see if we want to make a reduction in either cost or mass, we have to accept that we will increase the other. So if we reduce cost, we increase mass, and vice versa. But how do we then choose any one design amongst these if we have to trade off cost against mass? So a proposal in this way for reducing these two objectives to a single objective is to introduce value. Okay? So can we define value purely using the economics of the system? Okay? Can we translate what the market wants and what all of the stakeholders, or our primary stakeholders, are interested in to a single objective of value? So in this diagram, I've now overlaid it with a set of nominal contours which would define increasing value. And naturally, we can now see on our front of designs which are good in both cost and mass, equally good, we can't tell them apart, which direction we want to go in to achieve the greater value. And now we get 2 points. Our first point is where we satisfy our requirements whilst also achieving now the highest value. So if we follow the contours and we follow the curve, we arrive at a point which hits our requirement in mass and also has our highest value within that requirements box. However, we can also keep tracking that and find our location of highest value. However, we need to be able to negotiate the requirements. And at the moment in Discoverer, without a single customer, we're actually very flexible in the requirements that we can set or that we can implement. So we can actually start to look at concepts which really maximize value without necessarily having the requirements set by a single stakeholder or a single customer. Okay? We can actually try and find the concepts which are going to maximize total economic value. So, what do we need to do to drive to that point, or where can we see this? So, this is where Daniel, Sylvia, and Santiago are going to come in. We need to start to integrate these aspects of the market analysis, so where our stakeholders are, who they are, and how we can actually try and get from them what they define as value. And what business models or what concepts are actually going to help us achieve that. How do we measure the goodness or the value of any design? Well, we have to define value in the first place. Is it purely in dollars, or euros, or pounds? And how can we model this? Very difficult one. How do we feed in information? Is it purely from the design? Or is it, does it go up the chain? Does it come from the business models? Or does it come from the market analysis? Once we define that, how can we build models for that? And what level of detail do we need? Can we do this at a conceptual level? Or do we need to move into the much more detailed design phases before we can actually eke out this detail? And then finally, what would this look like when we expand it to the total VLEO system level? So I think we'll probably focus on this a little bit more later in the feedback session. But this is a kind of preliminary kind of idea of how we would link our various disciplines together. So looking from the EO market intelligence level, moving through business models and concept development, into mission design and system design, and then finally how we can feed back through to iterate towards higher value products, higher value propositions, higher value concepts. Where can we find the best Discoverer concepts? And finally, this is a little bit of a complex diagram to get your heads around. Certainly takes me quite a long time to look at it as well. But this is a representation of the value chain. So a lot of this comes into the stakeholders which you're interested in looking at. But if we consider ourselves as Discoverer in the middle layer, so our focus value layer, then we can imagine that there are many people who are feeding requirements into us at the top. So these people are influencing ourselves, stakeholders, but we also have many people that we, as Discoverer, can influence. So we can present concepts to people, use them, and at each level, we have values which we can look at. So to a component supplier of a new subsystem which is required for VLEO flight, we can add value by having suppliers which will make that component and sell it on. We have a value, or new VLEO systems will have a value in the middle there. And at the top we have all of the customers who are producing new data products from VLEO systems or new added value services. And then at the top we can also sum these up to see a total economic value across these levels. Now, actually identifying all of the layers in a system like this, in a diagram like this, is probably impossible. Or enumerating them in a way in which we can bring them all together. But how much of this can we look at? How many of the different stakeholders above and below can we identify and actually start to build in that we can look at the total value of VLEO concepts, and who ultimately is interested in building the total value of the system rather than just focusing on single levels in the system here as well. Okay. So I think this is maybe a little bit more of a thought-provoking proposition. We might hear a little bit about that in the feedback session, hopefully, but I think mostly we want to focus on this and how we can connect these different disciplines together. Because it's certainly not just a case of plugging in the numbers. So, think.